Okay, so good evening, everyone. Uh, this is a rerun of week three. For some reasons, it was not recording properly. Okay, whatever the classes I have taken, it was not recording properly. So I'll rerun it again. This video, or I'll re-record it again. Okay, so this is the uh, re-recorded videos. Okay, after the classes. Okay, so but I'll explain it again. Whatever we have done it in the classes. Okay. So, so last class and the last 2 to 3 weeks, what we have seen is we have seen starting from Lagrangian to Hamiltonian, then we go to photoelectric effects, okay, Compton effects, and finally to atomic and the spectra and so on. So, if you remember uh, properly, last time we are talking about Lagrangian in the first class, then we go to Hamiltonian. Okay, then we also talk about special theory of relativity. Then in the second week, what did we found out? We found out about photoelectric effect. Okay, then Compton effect, and also atomic spectra. Okay, so what we have seen is that we started first from Newtonian mechanics, then Lagrangian, then Hamiltonian, then SDR. Okay, then or special theory of relativity. Then we also have seen that there were some phenomena like photoelectric effect, Compton effect, in which classical mechanics cannot explain, and it has we have to add some more information or some more terms in it in order to explain the photoelectric and Compton effect. That is what we also assume, that a particle or a photon as a particle, okay, light as a particle. Okay, instead of considering the light as a wave, we also consider light as a particle. That's why we also introduced the formula h mu, okay, to be able to explain the phenomena such as photoelectric effect, Compton effect, as well as atomic spectra. So that was what we have done in the last two classes. And if you remember correctly, we also used the concept of Bohr's theory, right, to also explain of these atomic spectra and so on. But yes, there were few limitations in which these theory cannot explain. Okay, that is why we are moving ahead towards the new lectures, which is this week's lectures. Okay, so I'll just remind you again the books which I follow for these all the three lectures are concept of modern physics, Concept of Modern Physics by Arthur Beezel, and Quantum Mechanics by Zedley. Okay, so in these lectures, or in this today's we are talking about application. We will be talking about application of quantum mechanics. Quantum mechanics. Okay, now before we go that, okay, let's see few things. Limitation of Bohr's theory. Okay. Yes, Bohr's theory could explain atomic spectra and so on, but there are also few limitations in which it cannot explain. Okay, few of them or some of them are, okay, Bohr theory is applicable only to hydrogen, okay, only to hydrogen and one electron ions such as B plus, such as hydrogen plus. Okay, that means what does it mean? It means that it cannot explain, or it cannot explain other heavier elements. Okay, it can explain only hydrogen atom. Second, does not work for helium. Does not work even, I can say, even for helium. That means heavier elements Bohr's theory cannot explain. Okay, that is the second. The third is cannot explain why certain spectral lines are more intense. Okay, what do you mean by this? It means that, you know, what I have told you last class, that whenever there is a transition from the excited state to the lower states, a photon will be released, and those photons has a certain wavelengths. Okay, has a certain wavelength. When I say that why spectral lines are more intense, it also means, in other words, it also means that why certain transitions are most probable than the other transition. That means certain transitions are highly probable, whereas certain transitions are less probable. That is why, you know, Bohr's theory cannot explain why central spectral lines are also more intense compared to the other spectral lines. These are few of the limitations of Bohr's theory. Then comes in 1995 and 1926, right? Schrodinger, then Heisenberg, and Max Born. Okay, that is how, you know, these people starts coming, and that's how quantum mechanics also starts now the emerging and the more and more. Okay, so these two things in which I have shown it to you, these were the last two classes, and after the last classes we stopped with atomic structure, in which we also use Bohr's theory to explain some of the spectral lines. Okay, but then there are also limitations in which Bohr's theory cannot explain. That is why we are going to move ahead of the atomic spectra. But before I move ahead, I want to show you one basic difference between classical mechanics and quantum mechanics. Okay, so what is the basic difference? Okay, in classical mechanics, future, okay, future history of a particle can be completely determined by initial problems initial no, sorry initial position and momentum together with the force acting on it. Okay, what does it mean? It means that in classical mechanics, okay, according to classical mechanics or classical the physics, uh, the future state of the system or the state of the particle at any point of time we can easily determine. That means completely determine if we know the initial position as well as the initial momentum of the particle. Okay, that means at any time t we can easily find out what is the exact position and also what is the exact and the momentum. But according to quantum mechanics, what happens? Quantum mechanics deals with probabilities. Okay, it deals with probabilities. What does it examples? I'll give you example like Bohr's radius. Okay, Bohr's radius. Classical physics said the Bohr radius is a naught, which is equal to 5.3 into 10 to the power minus of 11 meter. Right? This is what classical physics says, that the Bohr's radius is exactly 5.3 into 10 to the power minus 11 meter. But quantum mechanics says no, this is not exactly entirely correct. This is the most probable radius. What do I mean by it? What do I mean by that? I mean, uh, suppose if you take different measurements, you will get slightly different values of the radius. It can be 5.8, 5.28, 5.3, 5.35, and so on. But 5.3 is the most probable and the radius according to quantum physics. That means if you take multiple measurements, you will likely get 5.3. There are also possible values that it can take 5.28, 5.35, and so on. Okay, but classical physics, just the exact value of the radius of the Bohr's radius is exactly 5.3 into 10 to the power minus 11 meter. So in other words, you can also say that classical physics is an approximation of quantum mechanics. Okay, so this is only a few things which I want to point it out before we move ahead. Okay, so now in quantum mechanics, I'll lay out some of the terms, okay, which is very important, okay, for solving numerical problems and so on. Okay, so the first term is wave function. Okay, wave function. So what is a wave function? So I will write it here. Point number A, the state of a system, the state of a quantum mechanical system, the state of a quantum mechanical system is represented by psi. That means if you want to find out what is the state of a quantum mechanical systems, is usually described by this wave function psi. So wave function psi describe the state of a quantum mechanical systems. Okay. Second, psi has no physical significance by itself. Has no physical significance by itself, but psi star, which is equal to psi star psi, represents the probability of finding the body at that time. Okay, that means psi by itself, okay, since it's a complex number, psi it has no physical significance, but the square of it, that means psi square, uh, which is a multiplication of a complex conjugate psi star into psi, represents the probability of finding a particle or of finding the body at that time. Okay, just I have told you that quantum mechanics deals with probabilities. Here also psi star psi represents or deals with the probability of finding the particle at that time. Okay, let me just make sure that it is recorded. Yeah, okay, I think it's recorded. Okay, fine. Now the next thing is normalization. Normalization, which is equal to integration, it is given by integration of psi star psi dx should be equal to 1. That means the total integration of your wave function psi star psi should goes to 1. This is the normalization condition. And third is the probability. The probability is p, let's say p of x1 comma of x2 is given by what? x1 to x2 psi star and dx. So if you want to find out the probability, okay, if you want to find out the probability, let's say at point from point x1 to point x2, you just need to integrate x1 to x2, okay, and multiply with a psi star and dx. Okay, so like I have told you, psi by itself has no physical significance, but the square of it represents or deals with the probability of finding the particle at that time. Okay, now we move to the next part, which is also very important. Okay, is Schrodinger equation. Schrodinger equation, and let's say this is a time dependent. So Schrodinger equation is one of the most important equation in quantum mechanics, because this Schrodinger equation tells you, okay, how does the state of the systems. Okay, just like you have different equation, right? Newton's law equation and so on. Here in quantum mechanics also we have what we call as a Schrodinger equation. And how does the Schrodinger equation looks like? It's given by minus of h cross squared by 2m del square psi by del of x square plus u psi is equal to e psi. Okay, this is in fact coming from your kinetic energy, this is in fact coming from your potential energy. Okay, and the whole derivation of this Schrodinger equation you can have a look. Okay, which is also available in the textbook which I have just given it to you, Quantum Mechanics by Zedley and Arthur Beezer. Okay, the whole derivation is given in there. Okay, the other one, the other equation, the other equation, Schrodinger equation, is time independent. Time independent Schrodinger equation. Okay, is given by d square psi by d of x square plus twice m divided by h cross square e minus v psi equal to 0. Okay, where v here is the potential. Okay, where v psi is equal to potential. So there are two very important equations. Okay, the time dependent Schrodinger equation as well as the time independent Schrodinger equations. Okay, I will not derive okay here because little long derivation. Okay, we'll just take only the final result. If you want the derivation, you can have a look, okay, at the reference book. Okay, now we will move, before we solve the problems, okay, the first problems and the second problems and so on. I will give you one show you one standard problem which is there in quantum mechanics, which is particle in a box. Particle in a box. Okay, so what does it mean, this particle in a box? So let me draw it. Okay, so let's say this is 0, this is x. Okay, particle in a box means the particle is free to move in between 0 to L. Okay, whereas at x is equal to 0, the potential V or U is goes to infinity, and at x is equal to L also is also equal to infinity. That means a particle that means a particle is free to move only in between 0 to L, but other than that it cannot exist, because the potential at x is equal to 0 is infinite, and also the particle and also the potential at x is equal to L is also infinite. So the particle cannot exist out of the box. The box is given by this one, 0 to L. This is the box 0 to L, so the particle cannot exist outside of the box. Okay, now particle is free to move between x equal to 0 and x is equal to L. That means it's free to move. There is no potential. Potential is equal to 0 between x equal to 0 to x is equal to L. But psi, the wave function, is equal to 0 for x less or equal to 0 and x is greater or equal to L. Why is it equal to 0? Because particle cannot exist outside of the box, right? So the total wave function, or the wave function in the region x less than 0 or equal to 0 will be equal to 0, and also the wave function at x is greater or equal to L is also equal to 0. So now let's write the wave function for this. Let's write the wave function. So these, let's write the Schrodinger equation, not the wave function, the Schrodinger equation, d square psi by d of x square. We have to solve this problem, and in order to solve this problem, we have to first solve the Schrodinger equation. Twice m divided by h cross square e minus v psi equal to 0. So our region of interest is between 0 to L. Okay, and in this region the potential is equal to 0 because there is no potential, and we are not interested to solve x less than 0 or x greater than L, because particle cannot exist there. So we are interested in the region 0 to L, and in this region what happens is that v equal to 0. Correct? Maybe let me name this as region 1. Okay, so in region 1 potential equal to 0. Now the Schrodinger equation will be d square psi by dx square plus twice m divided by h cross square, okay, e psi will be equal to 0, okay, because v is equal to 0, and then v term will be 0. So you can get d square psi by d of x square plus we can represent k square psi equal to 0. Here k square equal to twice m e by h cross square. Okay, so this is the standard differential equation. Okay, and the solution of this equation is simply psi equal to a any constant e to the power of I k x, okay, plus b e to the power of I k of x, where k is given by twice of m e divided by h cross square. Now let's name this as equation 1. Okay, there are two constants here, a and b. So we have to solve these constants a and b. So how do we do that? We have to use the boundary equations, boundary conditions. Okay, boundary conditions mean one of the boundary conditions psi equal to 0 at x equal to 0. Correct? Psi equal to 0 at x equal to 0. Then that means what happens? And psi is also equal to 0 at x equal to L. So we'll use, there are two boundary equations. Sorry, this is shy. There are two boundary conditions and also there are two constants, so we can solve this. Okay, first from a, I mean from 1, if we put psi equal to 0 and x is equal to 0, we will have what? 0 equal to a plus b. That means you can represent a equal to minus of b, or b is equal to minus of a. That means you can express b in terms of minus of a. And similarly, okay, if you use a minus b, then psi will be equal to a e to the power of I kx, okay, and minus, because why? Instead of b is equal to minus of a, so a equal to minus of k of x. So now there is only one constant term. Now what is the secondary boundary condition? Psi equal to 0 at x equal to L. Okay, that means 0 equal to a e to the power of I kl minus of a e to the power minus of I kl. Okay, and if you solve this problem, what happens then? You will get the value of a here. Okay, then you will get psi equal to root 2 by a sine of n pi by a x. Okay, that means you find the value of a and then put back in this equation. Okay, put back in this equation. Let me name this as equation. Let me name this as equation. Let me name this as equation 2. Let me name this as equation 3. Let me name this as equation 4. So put back whatever the value of a that you get from equation 4 in equation 3, you will get this one. So this is a very important results, okay, of a particle, moving freely inside the box. Okay, and the energy of such systems will be En equal to n square pi square h cross square by 2ml square. And from where do we get this? We get from this k square is equal to twice of me by h cross square. That means k square is equal to twice of me divided by h cross square. So this n here, n can go from 1, 2, 3, 4 and so on. Okay, so if you talk about the ground state energy, E1 will be simply pi square h cross square by 2ml square, since n is equal to 1. If you talk about the first excited state, what happens? We get E2 will be equal to 1. Instead of n, you have to put 2. So 2 square will be 4 pi square h cross square by 2ml square and so on. The second excited, third excited and so on. So similarly here, the wave function, the ground state wave function also, n will be equal to 1 for the ground state, n is equal to 2 for the first excited state and so on. Okay, so for symmetric potential, okay, for symmetric potential, that means v of x equal to, it's the same thing, it's just for a symmetric potential, infinity for x less than minus of a by 2, 0 minus of a by 2 x, a by 2, infinity x greater than a by 2, which what do I mean by this? It means that if I draw the potential in the box, it will be this will be 0, this will be minus of a by 2, this will be a by 2, and at this the potential is infinity. Okay, other than that, between minus of a by 2 to a by 2, particle can move freely. So the solution of such potential, I mean of such systems, is the same thing as what we have seen. It will be given by 2a sine of n pi by a x plus a by 2. A by 2 is the addition term, okay, in this problem for symmetric potential, which is also equal, we can separate this one into root 2 by a cos of n pi by ax for n equal to 1, 3 and so on, and root 2 by a sine of n pi by a x for n equal to 2, 4, 6. So even value of n is given by is related to sine function, and odd value of n is related to cos function. Okay, so let me just check it again. Want to make sure, yeah, want to make sure that the recording is going on tracks. Okay, now we will move to the first problem, okay, of your assignment. Okay, we'll move to the first problem of assignment. Just a second. Yeah. So the first question of your assignment, let me just read the questions. Okay. Uh, the wave function of a particle in a 1D infinite well of size 2a at a certain time is given to you. Okay, I hope you have the questions with you. The question is given that the wave function of a particle in a well, in an infinite well, one dimension of length 2a is given to you. Okay, so 1D infinite potential well of length 2a, okay, is given to be psi of x equal to a root 2 sine of n pi by a x, sorry, there is no n here, simply sine of pi by ax plus root 3 cos of pi by 2a x plus cos of 3 pi by 2a x. Okay, so now what is the question here? A is a normalization constant, and what is the question? The question is find the probability of finding the particle in the state n equal to 2 at that time. Okay, so it's a 1D infinite potential well of length 2a and is given to you, and also psi of x is given to you. So if such problems is given to you, okay, the first thing that you need to take into account is this a. A is a normalization constant, so you have to find out what is the value of a before you proceed any other calculation. So to do that, the step one is use the normalization condition to find out the value of a. That means, what is the normalization condition? Psi star psi dx, since it's a one dimension, equal to 1. But what is the integration? The integration, it runs from, since it is a infinite potential well of length 2a, so you can get minus of a to a. Okay, then what will happen to minus of a? Then you just put the value of psi star and psi. What is psi star? Psi star is a complex conjugate. That means if psi is I, then psi star is equal to minus of I. Okay, this example. But if this is a real part, then it is remaining the same thing. Okay, so what you need to do is that you can just replace a. So psi star again will be equal to a, okay, root 2 sine pi by ax plus root 3 cos pi by 2ax plus cos 3 pi by ax. Okay, so this is psi star, and we have to multiply again with psi. So we'll get a again, root 2 sine of pi by ax plus root 3 cos of pi by 2ax, okay, plus cos 3 pi by ax, and that will be total integration dx should be equal to 1. Okay, now if you look at this formula, okay, you have to multiply this term to this term to this term to this term and so on. You have to multiply. Okay, remember that the integration from minus a to a with sine and cos will go to 0. Okay, so what you need to remember is that you can do the integration only this to this, okay, cos to cos and cos to cos term. Okay, because the order integration will goes to 0. That means now you can just multiply a with a will be equal to a square, okay, a square, and then I'll also give on the sides integration from minus a to plus a of sine square pi by a x dx equal to a. Okay, so that means if I multiply this sine to sine square, and integration from minus a to plus a will get only a, but root 2 here and root 2 here are there, so we will do a. Okay, similarly here also cos term will be 3a, because root 3 and root 3 will be multiplied and cos square will be a, plus finally will be simply a the third term. Okay, so this is equal to 1. Okay, now if you look at it, get a square into 2a plus 3a plus a equal to 6a equal to 1, then you can get now a square equal to 1 by 6a, which implies that a equal to 1 by root over of 6a. Okay, so now once you know the normalization constant, you can replace back psi of x, whatever question is given. Instead of a, you can replace 1 by root over of 6a. Okay, and inside the bracket will be root 2 sine pi by a x plus root 3 cos pi by 2ax plus cos 3 pi by a x. Okay, so this is very important. Okay, this is very important. Now what you can do is that you can do the final problems, the final questions, which says that find the probability of finding the particle in the state n equal to 2. Okay, in the state n equal to 2, you go back to the one which I have just given to you for an asymmetric potential. For asymmetric potential here, for n equal to 2, what are the terms? Is only sign. Okay, other than that, for n equal to odd numbers, n equal to 1 3, you are talking about the cosine. So here there are both sine term, there are also both cos term, there are also both cos term, but the question asks for n equal to 2, so you need to solve only for this first terms. Okay, for the second if the question asks for the first and for the n is, let's say n is equal to 1, then you have to solve the cos sine term. Okay, n is equal to 1 or 3 and so on. Okay, but now since it is asked for n is equal to 2, so what you need to do is that you can multiply the multiplication constant, so you will get root 2 by root 6a sine of, again, since it is a box of length 2a, I can multiply 2 pi by 2a here. That means up and down by a constant, by a multiplication 2, plus root 3 by root 6a cos of pi by 2ax plus 1 by root over of 6a cos of 3 pi by ax. Okay, now what happens is that what you can do is that you can make in the form of equation, right, root 2 by a as given here, root 2 by a sine of n pi by ax. That means sine of pi by ax, which is equal to 1. So that means, how do you make this one equation? You can make 1 divided by 3, right? So this will be equal simply phi 2 of x plus 1 again, 1 by root over of 2 phi 1 of x, right? Because here n is equal to 1, here n is equal to 1 here. That means plus 1 divided by root over of 6 phi 3 of x. Okay, so you can express in the form of root 2 by a, root 2 by a sine of n pi by ax. But remember that here a is not simply a, but it is equal to 2a. Okay, so then what you can do is that now the probability of finding at n equal to 2 is what? Minus of a to plus of a, right? And you are talking about only the only the n equal to 2 terms, psi star psi dx, and this is equal to whole square. So what you can do, you will get only this term, 1 by root 3 into 1 by root 3, we get 1 by root 3 into 1 by root 3, which is in fact 1 by 3. Okay, because you are going to find only the state n equal to, what is the probability of getting the state n equal to 2 at that time. So it will be psi star psi, if you put the value of psi 2, again you will get the integration equal to be 1 minus a to plus of a. So that is why you have only 1 by 3 into 1 by 3, which is equal to 3. Okay, sorry, this is not square, simply psi star psi dx. Okay, so that is the total probability. Now let me just check. Okay, so yeah. Okay, so now what we can do is we can do the next problem. Okay, the next problem, that is the second problem. The second problem is also related to the first problem, but slightly different. Okay, so before we do that, let me just give you a little there are some terms in which you might need to understand. Okay, so question number 2, it says a particle of mass m is subjected to a potential v of x equal to infinity at x less or equal to 0 and minus of v naught delta of x minus of a for x greater than 0. Okay, so in your assignment it is given simply v naught delta x minus a. There is no negative sign. Okay, remember that you need to add a negative sign, otherwise this problem won't work. Okay, you need to add a negative sign. Okay, for x greater than 0 and v naught is greater than 0. Okay, find bound state equation. B-O-U-N-D, bound state equation. Okay, so this bound state, let me just explain it to you what this problems what bound state means. Okay, so solution. Okay, so before I solve the problems, let me just give you an idea of it. Okay, so let us consider this one. So that this is x and this is the potential v of x. So let me draw something like this, and let's say this is the potential. This guys is v1 here, and this one is v2, and this one is v minimum. Potential is minimum. Now suppose you have a particle of energy E which lies here. Okay, so this is the energy E of the particle, and this is the position x1 and this is the position x2. Okay, so if you look at it, particle can move freely between x1 to x2. right? But it cannot move outside of x1. Why? Is because the potential v1 is greater. Okay, so sorry. So what happens is that your particle can freely move between x1 to x2. That means it's bounded between x1 to x2 position. Why? Because the energy is greater than v minimum. The energy is greater than v minimum. As we have seen here, the energy here is greater than v minimum here. But it cannot move away or out of it because there is a potential v1 which is higher, and also on the right there is a potential v2 which is higher. Okay, so what I'm trying to say, bound state means bound state bound state occurs when particle cannot move to infinity. Okay, cannot move to infinity. That means it is bounded from one side and the other side also. Example here, v is greater than v minimum, but it is less than v1. Okay, because since the energy of the particle is less than the potential v1, it cannot move, but it's greater than v now, so it is free to move between x1 and x2. Another thing is unbound state. Unbound state means E is greater than v1 but less than v2. This is one unbound state. Why unbound state? Because E, since if E is greater than v1, that means I'll give you somewhere here, maybe somewhere here. E is greater than v1. That means it is free to move in the negative axis because it's greater than v1. Okay, even though it's less than v2, it is free to move in the negative direction. And the second is that E is greater than v2, right? If the energy E is also greater than v2, that means somewhere here the energy is greater than v2, then it can easily move away in the positive direction as well as the negative direction. So these are called unbound states. Okay, so now let's go back. Now I think you understand what is a bound state and what is an unbound state. That means energy should be less than a certain potential in a bound states. Okay, but in an unbound state, the energy is greater, okay, than the given potential. So now let's go back to your problems. Problems is given as what? Given as v of x equal to infinity of x less or equal to 0 and minus of v naught and delta x minus of a x greater than 0. So that means what you can, pictorially, I think you can look in the problem as this way. That means at x equal to 0, you have an infinite potential, and somewhere here, let's say this is the point A, you will have a potential of minus v naught, simply minus v naught. Okay, now like I have told you, in order to solve any problems, you have to write a differential equation. Okay, so what is the solution for x greater than 0? What is the Schrodinger equation? The Schrodinger equation is d square psi by d of x square plus twice m divided by h cross square v naught delta of x minus of a minus of k square psi equal to 0. Okay, so why? Is because you take it from the Schrodinger equation, twice m x squared e minus of e, but the potential is negative, so it will be coming potential, given potential is negative, so it will be positive, and minus of k square. Why I minus k square? K square I have represented simply minus of twice of m e by h cross square. Okay, instead of twice of m e by h cross square, I have represented with the negative sign. So negative sign again will go to the like your original equation. Okay, now for bound state, e is less than 0. Okay, this is very important. For bound state is less than 0, that means the energy should be less than 0. Now there are two positions here, x greater than 0, less than a. What happens when x is greater than 0 but it should be less than a? So the wave function is simply potential is equal to 0 because there is no potential between x greater than 0 and less than a. So you simply have a e to the power of kx plus b e to the power minus of kx. That means you just simply put this term, first term, equal to 0, and you can solve the Schrodinger equation. This is x greater than 0 but less than a. Okay, so let me name this as equation 1. Now for x greater than a, what happens? The Schrodinger equation psi2 of x, or the wave function after you solve the Schrodinger equation, the wave function will be simply c e to the power minus of k of x. Let me name this as equation 2. Okay, so now there are three constant, 1, 2, 3, a, b and c. And if you have to solve the Schrodinger equation, you have to solve this constants a, b and c. And for constants a, b and c, what you need to have three boundary of equations, just like we have seen in the first sections, that if you want to solve the constant a, b, you have to have two boundary conditions. Here also we have to use three boundary equations to solve the constants a, b and c. So first boundary condition, so now using boundary condition. Okay, what is the first boundary condition? The first boundary condition is that psi1, right, that is x greater than 0 less than a, at 0 equal to 0. Why? It's because your potential is infinite, so particle cannot exist at x equal to, so the wave function is equal to 0. Now if you put the equation, just like you have done, if you put the equation 1, that means psi1 is equal to 0, so you can get a plus b equal to 0. So you can easily represent it, b is equal to minus of a, right? So let me name this as equation 3. Then after that you can write so now after that, another boundary conditions is that at x equal to a, psi1 of a equal to psi2 of a. This is another boundary condition. I mean that x is equal to a, your wave function should be continuous. Psi1 is equal to psi2. Okay, that means now what happens? You can write from 1 and from 3, instead of b you can represent minus of a, right? Instead of b you can represent minus of a and put is equal to psi1 is equal to psi2. We can write a e to the power of ka minus, because plus b is equal to minus of a e to the power minus of ka. So the right hand side psi2 is given by this equation 2. You can write c e to the power minus of ka. So now we have reduced, you see, we have reduced to two constants now. Okay, so this is equation 4. Okay, now the last boundary conditions to solve is again at x equal to a, first derivative, okay, should also be equal. Okay, first derivative at x equal to a is what? Limit x tends to a psi2 star, okay, psi2 star a plus epsilon and minus of psi1 star a minus of epsilon plus twice m divided by h cross square v naught psi2 of a should be equal to 0. Okay, that means psi2 star minus of psi1 star. Okay, this will be equal to 0. Now you take the derivative of psi2 prime and then psi1 prime. What you will get is what? Minus of k, psi2 prime minus of k, c e to the power minus of ka, right? And minus psi1 prime we get k a e to the power k of a, okay, minus of k a e to the power minus of k of a, because psi1 is what? Psi 1 will be A and minus of B. Okay, now plus again twice M divided by H cross square V naught psi 2 of A. So instead of psi 2, again you can put with C e to power minus of Ka equal to 0. So let me name this as equation 5. So see, now what you can do is that you can use this equation C, which is equal to A e to the power K of A minus of A e to the power minus of K of A. You can represent it with you can represent it C, or C e to the power minus of K is A is equal to this term. So what you can do is that instead of C here, you can represent with A e to the power of K of A. So we can get minus of K, we get A e to the power K of A minus of K A e to the power K of A, okay, plus that means here substituting 4, this equation 4 in 5. Okay, so you get minus K e A e to the power K of A plus Ka, and then what else? We get minus of K A e to the power K of A minus of K A e to the power minus of K of A plus twice M divided by H cross square V naught, and then again instead of C you can write as A e to the power K of A minus of A e to the power minus of K of A equal to 0. Okay, so now here you can see that this term, second and third term, you can easily reduce to 0 because they will cancel one another. So we get minus K A e to the power K of A and minus of K A e to the power minus of K, which is remaining, plus twice M divided by H cross square V naught. Again the same thing, we get A e to the power K of A minus of A e to the power minus of K of A equal to 0. So you have seen now there is only one term, and every term there is A. So this you can remove A, and you will easily take the constant K equal to M V naught by H cross square 1 minus 2 e to the minus of 2 Ka. This is your final solution. So this is the equation of the bound state. Okay, that means if you want to find out like more, okay, you can still solve it, because K is again equal to minus of twice M e divided by H cross square, right? Whatever we have assumed, but okay, according to the problems we can solve up to here. Okay, K is equal to M v naught by H cross square 1 minus of 2 e to the power minus of 2 K. Okay, so because the question says find the solution, find the bound state equation. So the bound state equation is given by this problem, by this solution. Okay, so again this problem is also available in the ZLI book, ZATTI, the quantum mechanics books is there in the solved questions. Okay, if you cannot follow through, you can still look at it. There are step by steps, okay, explanation there also. Okay, now we will go to the third problems. Okay, to the third problems. Sorry, so just check how much we have done. Okay, so okay, we'll go to the third problems. Okay, so what is the third problems? The third problems is saying that consider a particle of mass m subjected to a 1D potential V of x equal to infinity for x less than 0 and half of m omega x square x greater than 0. But before I solve this problem, I will give you first one terms here is harmonic oscillator. Okay, because the third problem is related to a harmonic oscillator. Okay, so in harmonic oscillator, what is the difference is that the potential is half m omega square x square. This is how the potential, or if I want to draw it out, it will be simply something like this. Okay, so this is a potential v of x and this is x. Okay, so if I have to solve this problem, what do I have to do is I have to write the Schrodinger equation d square psi by d of x squared, right, plus twice m by h cross squared e minus, so v will be half m omega square x square. This will be equal to 0. Okay, and if you solve these problems, you will get something like the energy eigenvalues En is equal to n plus half h cross omega, where n equal to 0, 1, 2, and so on. So if you want to find out what is the ground state energy, Eg, simply n equal to 0, we'll have h cross omega by 2. If you want to find excited state, then we put n is equal to 1, we get E first excited state will be something like 3 by 2 h cross omega, and so on. Okay, so this is the energy eigenvalues of a harmonic oscillator. And the wave function, after solving this, you can write the wave function psi of x will be equal to 1 by root pi 2 to the power n factorial x naught e to the power minus of x square by 2 of x naught square hn of x square by of x naught. Okay, so this is slightly a lengthy equations. Okay, I will not derive it. All the derivations, okay, is available in the Zlib book. Okay, it's well explained there. Okay, I mean, it's a long derivation. I don't think so it's also really that necessary to remember each of these details. Most of the time it's usually given to you. Okay, and you can look this part in the Zlib book. Zlib harmonic oscillator. Harmonic oscillator. Okay, and this one hn of x naught, hn of x divided by of x naught, we can write as hn of y, in which h0 of y equal to 1, okay, and h1 of y is equal to y. Okay, and x naught square is equal to h cross divided by m omega. Okay, so if you solve any Schrodinger equations, okay, knowing the potential, you will get what is the wave functions, and also you will get what is the energy eigenvalues. Okay, so now we will go back to the problems number 3. Okay, like I have told you, let me just copy this one. Let me just copy this one. Just copy this one. Yeah, okay, so solutions. There is one difference between the potential which I have given it to you and this potential. These are also similar. Half of m omega x squared is is similar, it's the same, except that, you know, if you draw the potential, it will be this way. Why? Because at x equal to 0, you have infinity, right? But in the first, in the simple harmonic oscillator, you have half of m omega square in both the direction. But here, only in one direction, you have the term half of m omega square, because in the other side, x is equal to 0, your potential is infinite, right? So now, what is the question? The first one is find the ground state energy. What is ground state energy? Okay, the energy, okay, the energy eigenvalues of this type of problems is given by to be En is equal to 2n plus 3 by 2 h cross omega. Okay, the only difference between this and the normal harmonic oscillator is that in that case you have both sides half of m omega square x square. Sorry, this is half of m omega square, right? But in this problem is given only in one side, okay, half of omega square. Okay, so now what you have to do is that the energy is given to be 2n plus 3 by 2 h cross omega. The ground state energy, you know, n equal to 0. Here the same thing, n equal to 0, 1, 2, and so on. So n equal to 0, E ground state will be simply 3 by 2 h cross omega. Okay, now the subsection B says that find the expectation value of x. Find the expectation value of x. Okay, find the expectation value of x. So now, how do you find out the expectation value of x? So I have not given it to you. How do you find out the expectation value? So formula for the expectation value, suppose you have to find out, you have any a, you have any the quantity a. If you want to find out the expectation value, you will have to be psi star a psi dx divided by psi star psi d of x. But suppose if you have a normalized, a normalized wave function, then you can simply have a equal to psi star a psi dx. Now what we need is, we need to, now for our expectation, to find out the expectation of this, we need to have to find out what is the wave function psi. Okay, so if how do we do that? Okay, how do we do that? Now if you go back to the harmonic oscillator, you have this psi of n. Correct, you have psi of n. Now for the ground state energy, you need to put n equal to 0, and then you will get what is the wave function psi. So what is the wave function psi? If after you put n equal to 0, okay, you will get psi of 0 of x. I'll just write proportional, okay, proportional to x e to the power minus of x square by 2 alpha square. Okay, here alpha square means h cross divided by m omega. Okay, in the first term I have represented by simply x naught square, but you can also represent either x naught square or alpha square. It's just the same thing. Okay, now what you can do here is that you can write psi naught of x equal to constant a, x equal to minus of x square by 2 alpha square. Now you know what is the wave function. So what is the first step after you know the wave function? First you have to normalize out the value of a, right? So normalization condition first is normalization, okay, condition, that is what you have to do, 0 to infinity integration psi naught star psi naught d of x will be equal to 1, right? So you can write, if you multiply both sides, okay, psi naught star and psi naught, you will have a square integration from 0 to infinity, and x will do something like x square, right, e to the power minus of x square by 2 sigma square dx equal to 1. So this formula, okay, this is the standard formula in which you can get it from textbook. So or from any mathematical textbook is given as a standard form of 0 to infinity x to the power 2n e to the power minus of a of x square dx. This is in fact equal to 2n minus 1 factorial by 2 to the power of n plus 1 a to the power n root over of pi by a. So using this formula, what happens to our case? N is equal to 1, right? This n is different from your ground state. Okay, this n comes from your just mathematically here 2 into 1, so that is why n is equal to 1. It's not represent n is equal to 1 means first excited state. Okay, this is just to solve these integrals. N is equal to 1, and alpha and a here is equal to 1 divided by 2 alpha square. Okay, so use this equation, you will have a equal to 1 divided by root over of alpha cube 0. This is not 1, this will be a is equal to 2 and pi. Okay, you use this given standard equation, and that means And this integration 0 to infinity is actually equal to 2n minus 1 factorial by 2 to the power of n plus 1, and you substitute what is the value of a is equal to 1 by 2 of alpha squared and root over of pi by. You will get a is equal to 2 divided by alpha cube for, the square root of pi. Okay, now you know now what is the a constant. So now your wave function will be simply a into x, that means you have to substitute with this a term here, I mean the constant, the normalization constant, and you have to multiply with x square e to the power minus of alpha x e to the power minus of x square by 2 of alpha square. So now your wave function, if I have to write it, your wave function will be psi naught of x will be 2 divided by root over of alpha cube for pi, okay, x e to the power minus of x square by 2 alpha square. Okay, but what is the problem? The problem is find the expectation value. Now you know the wave function psi, so you can easily solve the integration. So the expectation value psi equal to simply 0 to infinity psi naught star and then x psi naught and d of x. I don't need to divide it by psi star psi because this is already a normalized wave function because we have already solved the constant a. So that means if you do this, you just need to substitute and then again use this formula. It will always come back. So you can get something 2 h cross by pi m omega. Okay, and also the question also asks you to solve the expectation value of x square. This is also the same thing. You can just 0 to infinity of psi naught star and then x square psi naught and d of x. You substitute the value of psi naught and multiply with x square and then solve the integration 3 by 2 h cross by m omega. Okay, and remember this problem you can use with the standard integral. No need to solve these problems because there is a standard integration for such set of problems that I have given to you. 0 to infinity of x to the power of 2n e to the minus of a of x square d of x. This is already given to you. Okay, and also there are problems which is given to you as x to the power of n e to the power minus of ax dx. Okay, there are such integration which is a standard equation. You don't need to solve, you just need to use the results from the standard integration. Okay, so this is what this question is all about. Find the ground state energies. To find out the ground state energy, you need to know what is the formula for the energy eigenvalues. And if you want to find out the expectation value, you need to know what is the wave function. Okay, as I've given to you the formula here. What is the wave function psi? And psi we have already derived. And if there is any normalization constant, you have to first put what is the normalization constant, then solve the wave function, then finally solve the expectation value. Okay, so I hope this is I hope you understand. Okay, all these three problems are always related. Okay, you have to solve what is the normalization constant. Okay, you have to solve what is the wave function, or you have to find the wave function, then finally you can find what is the, you can find it out whether it's a probability or the expectation value. You can use the formula. Okay, now we will do the last problems. Okay, and the next problems we will be talking in the next class. So the fourth problem, okay, which is also very important. Okay, before we go to the last problem, okay, I will give you a few formulas which is also required there. Okay, so till now we have talked only about Cartesian coordinates like dx, right? You have talked only dx. You have not talked about in spherical polar coordinates like r, theta, and phi. You have not talked about it. But in most of the problems, right, you will also encounter r, theta, phi problems. Okay, example like v of r is equal to simply r. Okay, which is dependence upon the r. Okay, not simply x or y or z. So in such cases, what you need to do, your Schrodinger equation will be minus of h cross square by 2m del square. It's not simply d square x y by d square psi by dx square. It will be del square in 3D plus the potential v of r. Okay, psi of r equal to 0. Psi of r equal to e of r. Okay, or I will say del square psi plus twice m divided by h cross square e minus v of r equal to 0. Okay, now again, if you want to solve this Schrodinger equation, you have to know what is the potential V of R, and you also have to solve what is del square. This is slightly much more lengthy. Okay, so del square is given to you 1 by R, del square R divided by del of R square minus 1 divided by h cross square R square L square. Okay, so from where do I got this? If you go back to I mean the Z ebook, okay, if you go to the Z ebook, you can take this chapter, three-dimensional problems, 3D problems in spherical polar, and there's also a hydrogen atom there also. So this is there, okay, is explained there. Okay, how do we get this del square and so on. Okay, for this this part of tutorial, okay, it's not necessary to go into the detail of it. I will just give you the important details. Okay, now L square is equal to minus of h cross square 1 by sine of theta del by del theta, okay, sine theta del by del theta plus 1 by sine square theta del square by del phi square. Okay, you see that there is an r term here, there is also a theta term here, and there's also a phi term here. Okay, so if you substitute 2, okay, and 3 in equation 1, let's say this is 3, you substitute, let's say 2 and 3 in 1, then what you will get? You will get something like minus of h cross square by 2m, okay, then 1 by r, because del square is 1 by r, del square divided by del of r square minus, so and minus will become plus, right? So we get 1 divided by 2m r square, right, L square plus V of r psi of r equal to E of r. Okay, if you look carefully, if you look carefully, what is the final solution of these problems? You can predict that, okay, your wave function psi of r should depends upon the radial part, okay, which is a function of r, and also the second part, which is a function of theta and phi. Okay, so that means any solutions of spherical polygons will always depends upon your radial part as well as theta and phi part. Okay, so again, mathematically, if you solve it, you can get phi part is 1 by root over of 2 pi e to the power of I m phi. Okay, and theta, which is a function of theta, is minus 1 to the power of m 2l plus 1 l minus of m factorial divided by 2 and l plus of m factorial plm cos of theta. Okay, that means y is, which is equal to l m theta on phi, is just a multiplication of this two term, which is equal to phi and theta. Okay, so from just like I have told you that from this quantum mechanics textbooks, okay, is already solved there. Okay, I can just write a few of them which is important to you. Y11 theta of phi is equal to minus of 3 by 8 pi sine theta e to the power of I phi. Okay, that means what you need to do is that you can just substitute what is the value of m to be equal to 1. Sorry, you can just substitute the value of m term of the value of m here, and the value of l to be equal to 1. So this is l equal to m, l is equal to 1, m is equal to 1, and you will get this type of equation. And you put if l is equal to 2, m is equal to 2, and so on, you will get different y value. Okay, and this ylm is actually called YLM is actually called as spherical harmonics. Spherical harmonics. Okay, so this is usually you will get it. Okay, more or less is the same. Okay, the only thing now, if you want to solve the wave function, your y of Lm is known, and you need to know only your radial part. Okay, this is different for different problems. Okay, depending upon your potential, which is a function of r. Okay, now let's move to the your final problems. Okay, question number 4. Okay, question number 4. So what is this question? This question is given to be a wave function psi of r is a x plus of iy e to the power minus of r divided by 2a naught. Okay, and what is a naught? A naught is given to you Bohr's radius. Okay, and a is real constant. Okay, as soon as you see a naught is equal to Bohr radius, automatically it comes to your mind that it is a hydrogen atom. Okay, so now the question number A says that is psi of r an eigenfunction of L square and Lz. Okay, again I'll give you on the right what is L square of psi is actually L plus 1 h cross square of psi, and Lz of psi is actually equal to m h cross of psi. Okay, now if you want to solve these solutions, okay, what you need to do is that you express, because this is x plus of iy, you can express x equal to r sine theta cos phi in spherical polar coordinates, and y equal to r sine theta sine phi. So now your wave function psi of r will be equal to a, right? And instead of x plus of iy, we substitute this x, and this is y. You will get r sine theta e to the power of I phi e to the power minus of r divided by 2 of a naught. Okay, what I have done is that you have also e to the power of I phi will get something like cos phi plus of I sine phi. Okay, so instead of cos phi plus of I sine phi, you can represent e to the power of I phi. And if you look carefully, what happens that psi of r now is proportional to what? This r term here, right? So that is proportional to r of nl, and also theta and phi term. We get y of lm of theta and phi. So which is proportional to? Okay, so for a hydrogen atom, okay, for a hydrogen atom, you need to know what is the value of r and l. So I will give it to you. For a hydrogen atom, you can look again in that textbook, or I can give it to you. R10 of r is given to be 2a naught e to the power minus of 3 by 2 e to the power minus of r divided by a naught. Okay, so that is for the R10. Next, R21 of r is equal to 1 by root over of 6 a naught cube r divided by 2a naught e to the power minus of r divided by 2a naught. Okay, so how do we know this R10, R21? I'll give you again. This is a very long problem, so I'll give you only the important details. Okay, you can go into the details, okay, into the derivation of it. Okay, so r and l for hydrogen, r of nl is given, r of nl is equal to minus 2 divided by n a naught to the power 3 divided by 2. Sorry, I will just write it here. R of nl is equal to minus 2 by n a naught to the power 3 divided by 2. Okay, and then n minus of l minus 1 factorial divided by 2n n plus 1 factorial whole cube 2r by n a naught to the power of l e to the power minus of r divided by n a naught, and then again we'll have something like l n plus 1 2l plus 1 2r divided by n a naught. Okay, so this is very lengthy equations, and that is how you get r10. That means you put n equal to 1, l equal to 0, r21 you put n is equal to 2, l equal to, and solve again, you will get this equation. Okay, so this is again available in the textbooks. Okay, all the details are there. Okay, I'll just give you this short few of them. Okay, so now if you look at it, okay, it depends on, in our case, r each points of r by n. So the radial part, it depends upon the radial r, depends upon the variable r, and e to power minus of r divided by n. So it's exactly this term here, r is equal to minus of r divided by 2 n. So you can represent r1 2 1. Okay, whereas y of lm theta phi, it depends upon sine theta e to the power of I phi. So sine theta e to the power of I phi, if you look again, sine of theta e to the power of I phi is y11. So that means you can write as y11 theta phi. That means here if you just write it again, we get n will be 2, l will be equal to 1, m equal to 1. Okay, so now why you need this one? Because you need to solve l square psi, which is given to you is l plus 1 h cross square psi. Okay, so this you don't need. Okay, this I just give you as a reference. You don't need this one to write. This you don't need. Okay, l square psi is equal to l plus 1 h cross square. So l is equal to 1, so you get 2 h cross square psi, whereas lz psi is equal to m h cross psi of r here, psi of r here will be simply m is also equal to 1, we get simply h cross psi of r. So that means psi of r, here we can write r here because it's a variable, it's a function of r. So psi of r is eigenstate of l square and lz. Okay, now the question, so now you know that you know the wave function psi is given to be r21 y11 theta phi, which is also equal to a r sine theta e to the power of I phi e to the power of r divided by a naught, right? You have the wave function now, and which is also proportional to this term. Now the second question is find normalization constant. Again, we are going to solve any normalization constant. Why? Is because since there is a term there, so since there is a constant term there, so we have to solve the normalization constant also. So but here the only difference is that we have to solve in 3D, not in 1D. Okay, so what does it mean? 0 to infinity, that is the r equal to 0 to infinity, theta will be equal to from 0 to pi, this is spherical polar coordinates. Okay, and phi equal to from 0 to 2 pi, and this again we get psi star psi d tau will be equal to 1. This is the normalization. And in the previous case we use psi star psi dx equal to 1, that is in 1D, but in spherical coordinates we have to use this formula. Okay, now what it also means, it means that 0 to infinity, 0 to pi, 0 to 2 pi. Okay, and psi star, which is, we can again you can express as a. Okay, and psi star, since it's real, you can just multiply again 2 times. It's just psi star psi, which is real, so you can just multiply it again. It will be something like r square sine square theta e to the power minus of 2r divided by of a naught, right? And this d tau is actually r square sine theta dr d theta d phi equal to 1. Okay, and then you can just solve this problem. R will be coming, r you will integrate differently, theta you will get differently, and phi will get differently. You get a equal to 1 by 64 pi a naught 5 to the power of 1 by 2. Okay, so now so that is your subpart questions. Find the normalization constant. Now the third is, see, find the mean value of r. Again, we are going to find out what is the expectation value of r, right? So again, r is given to you. What is the expectation value? I've just given it. I have given to you before. A is equal to psi, right? And r and psi, or it's equal to integration of psi star r psi d tau, right? And if it is already normalized, so you don't need to divide by psi star, right? Otherwise, if it's not normalized, then you have to divide by psi star psi. So r, that means here 0 to infinity, again 0 to pi, theta is 0 to pi, phi will be 0 to 2 pi, and will be something like psi star, and then r, and then psi, and then d tau. Okay, so if you do this, you will get a square, right? You will get, instead of a square, you will substitute this constant which you have already done. So we get, this is a square 0 to 2 pi of d phi, right? 0 to 2 pi of sine q theta d theta, and 0 to infinity of r to the power 5 e to the power minus of r divided by a naught dr. Okay, we just need to substitute this value of psi from this equation, equation, sir. You just need to substitute what is the value of psi, and the value of a you substitute from here. Okay, so that means if I want to substitute it, I will write 1 divided by 64 pi a naught 5. Okay, then d phi, integration of d phi will be something 2 pi into sine cube theta will be something like 4 by 3, and r5 again, if you integrate r5, e to the power minus of r divided by a naught dr will be equal to 5 factorial a naught 6. So that means we get 120 a naught 6, and if you solve this, you will get 5 a naught. Okay, again, this r to the power 5 e to the power minus of r divided by a naught dr is a standard problems of x to the power n e to the power minus of ax dx. Okay, there is a standard formula. Okay, if you want to check it out, there's infinity of x to the power n e to the power minus of a of x d of x. Okay, then you can find out what is the value of n. Here n is different, not the ground state exactly, like I have just mentioned. This is just for mathematically a value of n. Okay, now the last part of your this is the last part of this problem number 4 is find the most probable value of r. Okay, so most probable value of r, that means first of all you have to find probability. So probability is in fact given to be r square psi square. This is the probability. That means r square, and integration from theta will become from 0 to pi, phi will become from 0 to 2 pi. Okay, psi square sine theta d theta d phi. Okay, so when I say most probable value of r, it also means I will write here radial probability, and radial probability is actually probability of finding electron between r and r plus d of r. Okay, so now if you substitute again psi square and sine of theta, which is proportional to r square r4, not r square, r4 e to the power minus of r divided by of a naught. Why I'm not concerned about the theta and phi here is because we want to find out the radial probability. So theta and phi does not really matter much here, because what we are going to do is that for most probable we have to use the equation for maximum dp by dr equal to 0. That is why I don't, I mean, that's why theta and phi here doesn't matter that much, but only the r variable is very, very important, which is the radial value, which is a variable, radial variable. Okay, so now if you divide, if you differentiate, this is p, which is proportional to r to the power 4 e to the power of r by a naught, you will get d by dr, okay, r to the power 4 e to the power minus of r by of a naught equal to 0. This is a simply differentiation, okay, product differentiation. You can get something like r cube e to the power minus of r by a naught and 4 minus of r by of a naught equal to 0. So r, this r here cannot be equal to 0, otherwise the whole term will goes to 0. So we can get 4 equal to r by a naught, which is equal to r equal to 4 of a naught. Okay, so this is the complete solutions of your assignment question number 4. Okay, there is one questions which I will be taking next weeks. Okay, so remember these, whatever I have recorded now is re-recorded videos, because for some reasons the recorded videos which I recorded while taking the class, okay, was not running properly. So for those reasons I have to rerun, I mean re-recorded the videos. Okay, so it might be the way I have explained now and the way I have explained during the class might be slightly different here and there, but anyway, the notes I have already, all the notes I will provide for both of them. Okay, I'll upload in the drive, and if you have any questions you can always okay, mail me. Okay, and the next problem, which is the last problem, I will be taking the next week. Okay, so thank you.